Hello and welcome to my presentation. My name is Michael Spitzer and I would like to show you today our project-based learning scenario, how to construct, produce and assemble a planetary gear. At first I would like to introduce myself. I would like to introduce my research center and the project Facts of Workers. Then I will switch to the Planetary Gear project. I will talk about the background, the task description, the experiment, the target user feedback, the qualitative evaluation with the usability and technical experts, and last but not least, the evaluation results. As already said, my name is Michael Spitzer. I have a degree in computer science with focus on mobile and web technologies in context of technology-enhanced learning. Now I'm a PhD student in technology-enhanced learning and with focus on augmented reality. My previous work in the field technology-enhanced learning was the app TeamSketch, which is an iPad app to train collaborative learning by drawing a picture together simultaneously. As already said, I'm working at the Virtual Vehicle Research Center. Our main domains are automotive, rail and aerospace. We were founded in 2002 and we are around 200 researchers. I'm involved in the project Facts for Workers. The goal of the project is to build worker-centric workplaces in smart factories. We are the coordinator of this project, and the vision is to support the worker with data and information and knowledge in a worker-centric way. The goal is to empower the worker in his work, which should result in higher worker satisfaction and increased worker productivity. We face 4 different industrial challenges in this project. We would like to implement a personalized augmented operator. We would like to build worker-centric knowledge sharing and management systems. We implement self-learning manufacturing workplaces. And last but not least, we would like to support in situ mobile learning in the production. But how could we transfer a factory setting to a research lab? That's why we decided to implement a project-based learning scenario at our research lab. We transferred the user requirements and the environment from a smart factory, how to build a planetary gear, into our research lab. The motivation was to gain practical knowledge of challenges in construction, production and assembly. And also, how could we reasonably use new technologies in such learning scenarios? We chose the project-based learning approach because it's student-centered. The student should gain deeper knowledge of real-world challenges. The student should learn in an active learning scenario, and the students should learn to solve authentic problems. The approach for the whole scenario was that we started with the development of a project-based learning scenario. Then we evaluated the project-based learning scenario with one user of the target group, while improving the scenario iteratively. The next step was then to do a qualitative evaluation with experts with focus on the Smart Glasses app. Then we started to implement improvements of the Smart Glasses app. And the last step would be to evaluate the whole project-based learning scenario again with a larger group of users of the target group. The task was to construct, produce and assemble a planetary gear. Planetary gears are used in helicopters and, for example, in farm tractors. In the middle of the gear you can see the sun gear, and surrounding the sun gear the planets, and the outer gear is called the annular gear. We tested the whole project-based learning scenario with a 17-year-old student, high school student, who had a non-technical background, so he has no experience in CAD construction or production or assembly. The first step was to construct a planetary gear in a computer-aided design tool, in a CAD tool. The next step was to produce the missing parts with a 3D printer. And the last step was to assemble the planetary gear with the help of the smart glasses. Here you can see the parts we used for the planetary gear. So the annular gear is missing because there is not such a part available in Lego. So we decided to produce the annular gear by a 3D printer. We used the Platen Thingiverse, which is a platform for storing 3D printer parts. Everybody can download the parts and can print the parts by themselves. We converted the part to the computer-aided design tool so that we could use the part in our CAD tool. We used the tool Leocut, which is a computer-aided design tool specialized for Lego Technic. On the right side, you can see the part list. All available Lego parts are already imported to this tool, so users of the CAD tool just drag and drop the parts on the screen. So there's not a big challenge if you already know Lego Technic, which most of the children or participants of our group already know. So the users could focus on the tool itself and not on the parts. We divided the construction of the Planetary Gear in several subgroups. Here you can see the assembly group 1, and the student had to store all the construction steps within the CAD tool. This shows the construction of the sun gear. Then the annular gear, which was printed with the 3D printer. And then the planet group. The next step was to construct the rotor. And then the sub-assemblies were merged together. The rotor with the planets with the annular gear, and then the frame around the gear. So the student learned during this process that a normal assemble consists of several sub-assemblies, and they have to put together in a special order. The next step was to create an animation manual which could be used to train others to assemble this planetary gear. We used the tool Blender, which is an open source tool and is available for free, so everyone could download the tool and could use it in their lessons. The student created then a manual by himself and rendered it by himself. He didn't get any recommendation or any help from our side how to construct this video. The student decided the angle of the manual, the speed of the assembly steps, and also how many parts are assembled for each assembly step. And this was the outcome of the student's manual then. As you can see, the student decided different speeds. Also, in one section there are more parts assembled, in another section are less parts assembled. And also the angles. When the student assembled more parts, then he reduced the speed, because he already thought about that it would be more difficult if you have to assemble more parts than only one part. And then the student merged all the sub-assemblies together. So that was the task to create an animation video as an instruction. The next step was to assemble the planetary gear while using the smart glasses. We decided to use the ReckonJet glasses, and we implemented an app which shows these created manuals, and users could easily navigate through the assembly steps by using the touch pad on the side of the camera. It was very important that new videos shouldn't need any modification of the app. So we decided to use the smart glasses as a USB stick. You just connect it to the computer and copy the video file from Blender to the device, and also a text file which marks the assembly steps. So everyone could use this app without programming skills. Then I asked the student to build the Planetary Gear while using the app and to improve the assembly process in several iterations without any help. I would like to show you the last video from our student. The small picture-in-picture video shows the point of view of the user. He recorded it with the smart glasses. This video is also played twice as fast, just for time reasons. As you may already notice, the student decided by himself to separate the parts according to the sub-assembly. So then he is able to grab the parts faster. So the student learned a lot during this optimization process. As you may already see in the picture-in-picture video, sometimes it's very difficult to see how to assemble parts because the hands are blocking the view, so you have to somehow guess the assembly part. The main advantage of this approach is that you record the video in the point of view of the user, so it's more clear if you watch this video than a normal instruction video because you have the point of view of the instructor. During these iterations, there were some issues with the smart glasses, which should be mentioned. The smart glasses got very warm during all these tests. And also the dark glasses of the Recon Jet are not very good in closed rooms. But that might be the reason because the device is meant for sports activities, for outdoor activities, and that's why the glasses are dark of the Recon Jet. Now Recon is offering another device which is optimized for smart factory and assembly processes, which then has transparent glasses. So that's not an issue anymore. Then after the project-based learning scenario, I did an interview with our test person. The student said that the process to include the 3D printed parts in Leocut is too complicated. So we decided for the next iteration, we will convert the 3D printed part to Leocut. The cut tool was very easy to use for a student, even he had no experience in using CAD tools. The blend animation rendering was also easy to use for him after short introduction and training. But an issue was that the rendering took a long time. So a better approach would be that the student creates all the sections and then the teacher would render in a batch process all the videos then, and the student could do other things in the meantime. The student also gave feedback about the smart glasses. The student didn't like the dark glasses. Also the small screen and the blur was quite difficult for him, but this is only a hardware issue and the devices are evolving constantly, so this will be fixed in the future. Also, the device gets warm, and to set the focus between the display of the smart glasses and the actual workplace was in the beginning very difficult for him. But he said that after short training it was not a problem anymore. So the intended learning outcome of the whole project-based learning scenario was the students should gain knowledge of a whole production and development process. The students should learn to construct mechanical components. The students should gain CAD tool skills and should be able to produce not available parts with a 3D printer. Students should learn to create animations and how to assemble parts. Also, to gain smart glass experience was very important. Students should be able to optimize an assembly process and should be able to produce self-made assembly video instructions. After the learning scenario, we did a qualitative evaluation with 7 users, which are experts in usability and mechanical engineering. At first, we did a survey. We asked them for the age, gender, and their Lego Technic experience, also smart class experience, if they have any defective vision, and they also had to self-rate their fine motor skills, and last but not least, their technical experience. The first test was then a smart class fitting and a first impression test. I created a demo app where the users learn how to navigate with the touchpad and how to see correctly at the display and how to fit the glasses. Then there was a second survey. Users should give a first smart glasses feedback. They should rank the input techniques, quality, and also the different possibilities. And then they had to rate the display quality. The next step was to assemble a Planetary Gear with the assembly animation. They didn't get any other information about the Planetary Gear. They had just to assemble the Planetary Gear with the animation video. Then we did a second iteration with the recorded video from the assembly optimization process. And then we did a final survey, which was the same as the second survey, but with additional questions about the general feedback. The evaluation results of this approach was that most of the users had already Lego Technic experience, so they know the parts and they know how to assemble Lego Technic parts. For the input possibilities, the touchpad was most popular. Then hand gestures were mentioned, and then head gestures, and the last rated was speech. That was very interesting because most of the users didn't like to speak to the glasses. They don't like to speak without any person there. Looking at the LCD screen of the smart glasses was very exhausting for most of them, especially when they had to use the glasses for a longer time. Most of the users think that the animation video was easier to follow than the recorded video instructions, but the recorded video instructions are better to transport personal knowledge, so you can communicate assembly tricks, for example. It was very interesting. One participant during the study suggested a better assembly strategy. He recorded a better assembly strategy with the smart glasses, and now we have an improved assembly video. So that is a good example of how to transport implicit knowledge. I also asked them for ideas for improvement of the smart glasses app. Some users had difficulties because I didn't implement the pause function. Some of the users were stressed then, because I implemented the section change, so users could easily go back one section and repeat one section, but not a pause function. So in the next iteration, we added a pause feature by tapping on the touchpad. Also, the assembly sections are difficult to identify for the users. They don't know in which section they are. Is it the first step, the fifth step, or the 10th step? So the improvement will be that we will add numbers on the screen for the current assembly section, so the user know in which section he is at any time. Also, that the assembly instruction loops through all the sections was a problem for some users, because if you want to do a backward jump from the first video to the last video, you have to scroll through all the videos again. So I will add a possibility to jump back from the first to the last section. Some users complained about the speed of the assembly instructions. Some were too fast, some were too slow. So I will add the feature that users could increase and decrease the speed of the section. Also, the angle of the animation instructions makes the assembly process difficult in some situations. So I will implement a hand gesture to change the angle of the instruction. It was also very difficult for during the assembly videos that users can see every part. So in the animation, we will gray out some of the not used parts, so the user had to focus on the currently active part. The future work within this project will be to improve the Smart Classes app and to evaluate the whole project-based learning scenario with more users of the target group. Thank you for your attention. Please don't hesitate to contact me at any time for recommendations or other information. Thank you.